Okay, all right, good afternoon, everyone. So just a couple of housekeeping things before we start with our new lecture topic here this morning. So hopefully you have not forgotten that we are currently in the midst of Term Quiz 2. So your deadline to submit that is 11:59 p.m. tonight, so don't forget about that. Once we, so the marks for that will come back tomorrow morning, and then that puts us into the 3-day period for rebuttals. If you, again, kind of look over your exam and then decide if you're going to make a rebuttal, and you have until the end of Friday to do that. Aside from that, I mean, the short communications continue. I know that, people are getting feedback, so they're being marked. Again, I keep having lots of conversations about interesting ideas. My biggest reminder here, especially if you have not yet started, is, again, and the Module 2 video highlights this, but again, check out and see what HumMod can do before you start pitching ideas, right? Because I know there have been a couple of groups, they've submitted ideas, and the feedback has mostly been, HumMod can't do this. So don't spend a lot of time pitching an idea and submitting a module for a project that you will never be able to simulate. It's emphasized in the Module 2 video to make sure it's HumMod doable. So make sure you've got HumMod downloaded, you're playing around with it, you're seeing what it can and can't do, and pitching projects that are doable through that software. Questions about things before we jump into the lecture here? Everybody's all good? Okay, all right. Okay, so we are starting up a new topic today, continuing on the theme of nervous physiology, but moving on to talk about electrophysiology. And so where I want to begin with this is with a couple of overview slides here. So this is a familiar looking figure to us, hopefully, because it came up a couple of times in the previous lecture topic. I was using it before just to talk about the different regions of neurons. And what I'm going to do is use the same diagram here to give us a bit of an overview of the electrophysiology of neurons. So basically this slide here is kind of the template, if you will, for really the next several weeks of this course and all the things we're going to talk about over the next few weeks. So what I really want to think about here on this slide is how does nervous communication work? And so we'll start by thinking about how does nervous communication take place inside of a neuron, so kind of within neurons. And the fundamental answer to that question is that nervous communication within neurons occurs via electrical conduction. And so when we talk about electrical conduction, we're talking about how charged species of some kind are going to be moving around within the neuron. Predominantly, we're talking about ions as our charged species. And you're going to see a little bit later today, roles for sodium and potassium and, chloride ions and calcium ions. This is fundamentally how nervous system communication occurs within neurons, is through the movement of these various charged ions. The kind of starting point for this whole electrical conduction mechanism is the resting membrane potential, which we're going to be focusing on here in just a moment. As it says here, and as you probably already know, the resting membrane potential is such that there's this negative charge on the inside of the neuron, and then there's a positive charge on the outside of the neuron. And so we're going to talk, as I said, in a second about kind of why and how that is. In response to a stimulus, and I want to define stimulus here because it's a term that is used so frequently in nervous physiology. So a stimulus we can define as a detectable change in the internal or external environment. And you'll notice, and I want to put emphasis on the word detectable here, in order for us to detect a change in our external or internal environment, we have to have some kind of receptor expressed within our neurons that can actually detect, this parameter that's changing. And if we don't have receptors for these things, then ultimately we can't detect these changes, right? We can only sense and perceive the things that we have receptors for. You know, a good example of this would be to think about light, right? Within the retina of our eye, we have receptors that can detect visible light, right? So that hence I can see all the, you know, reds and blues and greens and things that are in my environment. But as far as humans go, we don't have receptors for infrared light, and we don't have receptors for ultraviolet light. And so even though there's infrared light and there's ultraviolet light in this room right now, I'm not consciously aware of it because I don't have the receptors that can detect it, right? So when we talk about a stimulus, we're talking about, you know, sensory information that we can actually detect because we have some receptor expressed within our neurons that is capable of detecting that particular sensory information. So that's a stimulus, and so in response to a stimulus, and we know that these stimuli are detected predominantly within the dendritic zone of neurons, so the cell body and the dendrite. If we subject a neuron to a stimulus, then we're going to see the membrane potential shift from its resting value to some new value, and that new value we call a graded potential, right? So graded potentials are kind of these membrane potentials that occur in response to a stimulus, right? A change in the membrane potential away from its resting value to some new value as a result of a stimulus. And we call them graded potentials because, as we'll see a little bit later, the magnitude of the change in membrane potential in response to a stimulus, you know, it's basically directly proportional to the strength of the stimulus that's causing it. And so if you think about light, obviously we can have very different gradations of light. It can be dark and then a little bright, a little brighter, and very bright. Like we have these different levels. We correspondingly will get these same kind of gradations in the membrane potential change that we observe in response to those different, say, gradations of light. One thing that's important for us to appreciate then here too is this idea of what's called transduction, because what these receptors that I was talking about moments ago that allow us to detect these various stimuli like light or sound or touch or whatever other stimuli you can think about here, what's cool about these receptors that detect these stimuli is how they transduce those stimuli into an electrical phenomenon, right? That all the stimuli that our neurons are subjected to, we translate or transduce those stimuli into an electrical change, a graded potential, right? So you can think of the various sensory receptors we have as translators, right? Neurons speak the language of electrical conduction. Neurons don't speak the language of light and sound and touch and all these things. They need a translator to translate or transduce those various stimuli into an electrical signal that neurons understand. And so we're going to talk more about that again probably later in the week when we talk more about graded potentials, but I wanted to kind of introduce the idea at least now of transduction, this ability that neurons have through the receptors they possess to turn, you know, non-electrical stimuli, again, light, sound, touch, pressure, whatever, into electrical signals, these graded potentials that we've talked about. We also have to appreciate that graded potentials can be either excitatory or inhibitory. So excitatory meaning that they are going to increase the chances that this neuron is going to generate an action potential, and inhibitory the opposite, decreasing the chances that this neuron is going to generate an action potential. And so again, we'll go into more detail about what determines that later on. We also know, and we talked about this in the last couple of weeks, that there can be, of course, many stimuli acting on the dendritic zone of a neuron at a given time. Again, I point out all these green sort of synaptic inputs from other neurons here. And what we recognize is that we can have all these many graded potentials being generated simultaneously within the dendritic zone of this neuron. And all of these gradient potentials ultimately have to travel from wherever they are first initiated. They have to travel to this region of the dendritic zone called the axon hillock. And we have noted before that this is where the integration of all those gradient potentials into basically a single gradient potential is going to occur. And again, we'll go through that summation process a little bit later in the lecture. This overall integrated summed gradient potential that is generated here within the axon hillock is then kind of fed forward into the axon initial segment. And here, if that gradient potential in this region, in this axon initial segment region, if the gradient potential gets us to or above some threshold potential value, then that is going to lead to the generation of an action potential right there within the axon initial segment. And then, as we've already talked about, once that action potential is generated within the axon initial segment, the action potential will then be conducted along the length of the axon and all the way into the telodendritic zone and all the many axonal branches that are there. And then at this point, we now can think about the synapse, right, which is this connection between neurons, or between neurons and skeletal muscle cells or glandular cells. And now we're starting to shift towards thinking about the communication not within neurons, but now the communication between neurons and between neurons and muscles and glands. And so synapses are this interface between neurons or between neurons and muscles and glands. And there are three parts to every synapse. The first part is what's called the presynaptic neuron, right? So this would be the neuron that is going to be basically sending a signal out to try and stimulate or inhibit, I suppose, another neuron. We have the postsynaptic neuron. So this is kind of the receiver here. It's the one that's going to be stimulated by the output from the presynaptic neuron. And then we have the synaptic cleft, which is this like space that exists between the pre and postsynaptic neuron. So every synapse has these three components. And if we think about how does communication across the synapse between neurons occur, it can occur by electrical conduction. So in some cases, we do actually have ions that will, flow out of the presynaptic neuron and flow across the synaptic cleft and flow right into the postsynaptic neuron and directly alter its membrane potential. But more commonly, especially in, say, the adult nervous system, the mechanism of communication between neurons at the synapse would be chemical transmission, right? That you would have a chemical agent that is released by the telodendritic zone, and then it diffuses across the synaptic cleft and binds to a receptor on the dendritic zone of the next neuron. And of course, as you already know, those chemical agents are neurotransmitters. That's what we call them, right? So neurotransmitters, and we're going to have an entire couple of weeks of lectures about various neurotransmitters. These are the chemical signals that are going to be released from the postsynaptic neuron, diffuse across the synaptic cleft, and bind to their corresponding receptor on the postsynaptic neuron. And sometimes these receptors are then going to, directly allow ions to flow across membranes. So again, we can convert the neurotransmitter signal back into an electrical signal, which neurons recognize. And in some cases, these receptors, when the neurotransmitter binds to them, they may start an intracellular signaling cascade that ultimately culminates in, usually again, some kind of ion flowing across the membrane. So this gives us an overview of kind of a roadmap of sorts for where we're headed over the next several weeks in this course, kind of systematically going through the various parts of this diagram so you can hopefully come away with a pretty full and exhaustive understanding of how neuronal communication works. Before I dig into resting membrane potential a little bit further here, there's another overview slide that I wanted to bring here I think is important. And this is for us to talk about the various body fluids that we have within the human body. This is very directly relevant to the conversation about membrane potential, because we're going to be talking about, different body fluids and, ion flow between them and charges and all these things. And I just want to make sure that we all are on the same page here with respect to our understanding of the interrelationships between these different fluids. Because I've learned from experience that sometimes if we don't cover this explicitly, then sometimes some people get a little bit lost here. So there are three major fluids that are highlighted here on this figure, and where I'll start here is with what's called the intracellular fluid. It's also known as the cytosol. So these are two synonymous terms. And obviously we're talking about the fluid that is contained inside the cells, right? So it's just the fluid that's inside the cells. Nothing more to say about that. And then in contrast to the intracellular fluids, we have what are known as the extracellular fluids, which are obviously the fluids that are outside of the cell. But you can see here in this figure that there are two major extracellular fluids that we have to think about as we embark upon this discussion of nervous physiology. The first is the blood plasma. So this is the extracellular fluid that is contained within your blood vessels, right? It's this intravascular fluid, if you will. And then the other extracellular fluid is the interstitial fluid, right? Which is the fluid that is outside, the extracellular fluid that is outside of your blood vessels, and is the fluid that is directly in contact with the cells. It is the fluid that is directly bathing the cells, this interstitial fluid. So again, these are both types of extracellular fluids. It's just one's confined to the vasculature and one is outside the vasculature and bathing our cells. And what we have to appreciate about these two fluids, as they demonstrate here in this figure, is that these two fluids, the blood plasma and the interstitial fluid, they freely exchange ions between them, right? Again, we just said that ions are so critical to the electrical conduction mechanism of neurons, and so it's important to realize that ions can freely exchange themselves between the blood plasma and the interstitial fluid. The reason that's so important to understand in nervous physiology is because in nervous physiology, when we talk about extracellular fluids, I mean, we're mostly talking about the interstitial fluid because that's what's in direct contact with, the neurons, and it's the fluid that is directly on the outside face of their cell membranes. But we have to appreciate that the ion concentration of that interstitial fluid is equal to the ion concentration of the blood plasma, right? You hardly ever, if ever, see any kind of disequilibrium of the ion concentrations between these two fluids. And that's important because very commonly in a clinical setting, we're not going to be making measurements of your interstitial fluid, right? You've probably never gone somewhere and had them draw your interstitial fluid to measure its ion concentration or any other characteristic, because in fact, it's a pain in the ass to do, right? It's a very technically challenging thing to do, but there's probably a very good chance that you've had blood taken for clinical analysis, right? Blood is easy to get, right? As long as you have, a trained phlebotomist who doesn't butcher the hell out of you trying to get a needle in your veins or yell at you that, do you drink enough water? Because I can't find any blood here, right? Which is the story of my life every time I get blood taken. But anyways, I digress. Blood sampling is what we do. It's clinically the easy thing to do here. And so what I really want to emphasize is if you're making measurements of ion concentrations in a blood sample, you can assume that the ion concentrations in the interstitial fluids of the body will be identical, okay? So I really want to emphasize that point. The other thing that I like about this figure that I want to emphasize is how it reminds us that the ion concentration of our blood plasma, and therefore our interstitial fluid, is influenced by the action of the kidneys and also by our diet and the action of our gut. Right, this is important to keep in mind. We can manipulate, to some extent, the ion concentrations of our blood plasma and interstitial fluid through our diets, right? Through the ions that we consume, right? The various salts, we think about how salty the food is that so many of us eat and how that can influence the concentration of sodium and chloride, for example, in our blood plasma and interstitial fluid. And similarly, we have to appreciate the role the kidneys play in regulating our blood ion and therefore interstitial fluid ion levels. Right? The kidneys, as they demonstrate here, are able to pick up and remove ions from our blood plasma to help us to regulate our blood ion and therefore interstitial fluid ion concentrations. And correspondingly, you know, if there are issues with your kidneys, right, this can manifest in terms of issues with the nervous system, right? Because suddenly if the kidneys aren't regulating extracellular fluid ion levels properly, then this can lead to changes in those ion concentrations that can change the value of membrane potential in ways that could either excite or inhibit the nervous system. So it's important to realize the influence that diet and kind of the absorption of ions plus the regulatory mechanism of the kidneys can have in terms of nervous system function. Okay, with all that overview in our heads now, we can jump a little bit more into the details here. Let's start by talking about resting membrane potential. The figure that I have here gives us a definition of resting potential. It says it's an electrical potential difference across the plasma membrane. So we're going to dive into that a little bit more here, but we're basically saying that, you know, there are different charges across the cell membrane, that the cytosol and the extracellular fluid have slightly different charges. So how does this come to be? Well, let's take a bit of a step back here and focus on another part of this figure. It tells us in this figure that if you were to look at the extracellular fluid or you were to look at the cytosol, these two fluids would have equal numbers of positive and negative charges within them. And this is because of something called the law of macroscopic electroneutrality. This is a law which tells us that overall, an ion solution is electrically neutral. So we can think of our extracellular fluids and our intracellular fluids as fundamentally ion solutions because they have lots of ions dissolved in them. And so the law of macroscopic electroneutrality tells us that when you look at an ion solution overall, it will be electrically neutral. It will have equal numbers of positive and negative charges consistent with what is mentioned here in this figure. Now, having established that there are equal numbers of positive and negative charges in these fluids, we can equally appreciate that the concentration of the different ions within these two fluids, the cytosol and extracellular fluid, are not necessarily equal, right? And we're going to talk more about this in a second, but I'll give you just as an example now, potassium. Potassium is actually in a way higher concentration in our cytosol than it is in our extracellular fluids. And so notwithstanding the fact that there's no difference in the net charge of the cytosol and the extracellular fluid for the most part, because potassium is more abundant in the cytosol than in the extracellular fluid, potassium wants to leave the cytosol and cross the membrane to go into the extracellular fluid, as my arrow indicates. And that happens. Potassium is constantly leaking out of our cells and into the extracellular environment. And because potassium is positively charged, as it leaks out, it's obviously going to make the cytosol negatively charged and make the extracellular fluid positively charged by its movement. Now you might then say to yourself, wait a second, if that happens, then doesn't that lead to a violation of this law of macroscopic electroneutrality? And the answer is, strictly speaking, yes. And so we're going to modify the law here with this little extra word. We're going to say that this law says that overall an ion solution is approximately electrically neutral. So this law doesn't really require like strict accounting to balance the books ion to ion. You know, it's not a corporation that needs to balance its books down to the last penny. The law of macroscopic electroneutrality basically says the ion solution has to be pretty damn close to electroneutrality, but a few ion differences here or there doesn't make much of a difference. It has to be just approximately electrically neutral. So it allows for there to be this movement of some ions across the membrane to then create a negative charge on the inside face of the cell and a positive charge on the outside here of the cell, as I've indicated now. And so because we have more positive charge on the outside of the cell and more negative charge on the inside of the cell, we say that cells are polarized, right? That they have a positive pole and a negative pole, right? It's positive on the outside face of the cell membrane. It's positive in the extracellular fluid, but it's negative on the inside face of the cell membrane, negative in the cytosol. So we use that term polarized to refer to this charge difference, this membrane potential that exists across the plasma membrane, all right? And so what we also have to appreciate is that this charge difference is not just confined to the region around the membrane, which is kind of what this picture is implying, but it's not true. It's not confined to the region around the membrane, because what you can imagine is a positively charged potassium enters into this little region of extracellular fluid next to the membrane. Well, you can imagine that negative charges out here in the bulk fluid would be attracted to that positive charge, so they might shift over towards it. And then suddenly this region here becomes a little bit more positive, and maybe negative charges here come in to see that positive charge, and this becomes negative. Hopefully what you can kind of imagine here is that both in the extracellular and in the intracellular fluid, any charges that form within that fluid will basically be, spread throughout the entire fluid, right? Because as soon as you have, some charges, like some negative charges building up here against the membrane, it's going to lead to shifting charges elsewhere in the cytosol in that case. And ultimately, as charges are shifting, other charges shift, and ultimately the whole entirety of the cytosol becomes effectively negative, just like the whole entirety of the extracellular fluid could become positive. You can't really confine these charge differences to just the membrane. There's nothing to stop them from spreading throughout the entirety of the fluids. So effectively we're saying that the entirety of the extracellular fluid will be positively charged, the entirety of the cytosol will be negatively charged because of this movement of charged ions, like in this case potassium, moving across the membrane to follow their concentration gradients. The next question, of course, and why I emphasize that this charge spreads throughout the entire fluid, is because it leads directly to the next thing I want to talk about, which is how do we measure this charge difference, this resting membrane potential that exists across the cell membrane. We measure it using a device called a voltmeter, right? And at a very fundamental level, the voltmeter that you might use to measure resting membrane potential in a cell, I mean, it's fundamentally no different than the voltmeter you might have at home, to check out how much power is left in a battery, or make sure that the electrical outlet is, disconnected from the power before you try to, piss around with it or something. It's fundamentally the same device, obviously in this case, structurally customized to work with cells. But the way a voltmeter works here is you've got these two electrodes. So there's a reference electrode and there's a recording electrode. The reference electrode is placed into the extracellular fluid. Okay, so it can be placed anywhere in the extracellular fluid because, again, the whole fluid is going to have the same charge. You place it into the reference electrode into the extracellular fluid, and then you place your recording electrode into the cytosol, which obviously means you have to penetrate that electrode through the cell membrane to get it into the cytosol. And then what the electrodes do is they basically measure electrical potential of the fluid that they are present in. And the way they do this, kind of just in a very kind of theoretical way, is they take a charged species, so this positively charged thing here, right? Imagine that's inside the electrode, and they're going to try and push it into the fluid surrounding. And they're going to basically say, how much work do I have to do to push this charged species, this positively charged species, into this fluid surrounding the electrode? Obviously, if the fluid surrounding the electrode is positive, then pushing a positive charge into that fluid is going to require a lot of work because like charges repel each other. And obviously, if the fluid around the electrode is negatively charged, then it actually will not take any work at all. In fact, there'll be kind of negative work done if you push a negative charge into that positive space because those two charges want to come together. So fundamentally, that's what the electrode is doing. It's trying to assess how much work it takes to push a charged particle into this surrounding fluid. The reference electrode figures out this work and then kind of sets it to a value of 0. So here it says the reference electrode will have a value of 0 millivolts. So basically, it will figure out how much work did I have to do to shove this charge into this space, right? If it then divides the work done by the charge, it figures out the electrical potential, and it just sets that value to 0. That's what we call it, the reference electrode. It's just saying whatever electrical potential I've measured here, however much work I had to do to shove this charge into this space, I'm going to set that value as 0 electrical potential. The recording electrode then does the same thing, right? Figures out how much work it takes to shove the same charge into this cytosol, but then whatever value for electrical potential that it comes up with, it sets that, that's what it displays, right? So essentially what shows up on the display here, this negative 70 millivolt value, is a measure of, what is the electrical potential inside the cytosol compared to the electrical potential in the extracellular fluid, and the latter extracellular potential there in the extracellular fluid, we have just arbitrarily set that to 0, okay? So it's basically telling us again, what is the difference in electrical potential between these two fluids, which we said is the definition of resting potential. Another thing you might be thinking here is, well, could we not just flip these electrodes around, put the recording electrode into the extracellular fluid, put the reference electrode inside the cytosol, and then of course, presumably we would get, the exact opposite measurement, positive 70 now. Why don't we do that? We don't do that because it would be confusing as hell. So it says here, by convention, meaning by agreement of all physiologists, and you're now implicit in all of this, you have to agree before you can continue on this course any further that you will uphold this. You will always measure your resting membrane potential by putting the recording electrode inside and putting the reference outside. So you're always measuring the inside potential relative to the outside, which we've set to 0. All right? So that is the established convention. Yes, you could do it the other way, but we all have to agree to do it one way, otherwise it's very confusing, right? Because you're saying, well, I measured resting potential at positive 70, and she says, well, I measured resting potential at negative 70, and we're all confused as to like, why are these different cells having such different potentials? We all have to agree from this time forward, we're gonna measure in the same way, okay? Everyone's in agreement? Perfect, okay. Okay, so that's kind of how we measure the resting membrane potential. The next thing to kind of establish here is the fact that, as it says here, all cells have a resting membrane potential. So all cells are polarized, positive on the outside, negative on the inside. This is not a unique property of neurons. And this is something that has to be emphasized because, I mean, the only time we ever seem to talk about resting membrane potentials is in the context of nervous physiology. And so, of course, that creates this mindset as a student of the discipline that, oh, resting membrane potential must be something that's unique to neurons. We only ever talk about it when we're talking about neurons and nervous physiology. But I want to explicitly say it's not true. Every cell in your body has a resting membrane potential, right? And so here I have this table showing us how the value of that resting membrane potential can vary among cell types. So here, for example, neurons very typically have resting potential values kind of negative 60 to negative 70 millivolts. But you can see that some cells, like skeletal muscle cells, have more negative resting potentials, negative 95-ish. Other cells, like say the red blood cells, the erythrocytes, they have resting potentials that are closer to 0 at negative 9. And again, these are all just kind of approximations and ranges, right? I mean, these values are, I wouldn't sit there and memorize the table because these values are quite variable. But the point I'm trying to make overall here is that, again, all cells have a resting membrane potential. And even the magnitude of that resting membrane potential is variable among different cell types and even variable within cell types under different conditions. So the question to then sort of think about next is, well, why? Why do all cells have a resting membrane potential? as far as neurons go, we have some sense that they're using this as part of their nervous communication mechanism. But what about other cells? Why do they have a resting membrane potential? And the fundamental answer to the question is because the resting membrane potential, not only does it represent kind of this charge separation that exists between the cytosol and the extracellular fluid, it also represents the amount of energy that is released when we let charged species move across that cell membrane. So what do I mean in this case? Well, if it's positively charged in the extracellular environment and it's negatively charged in the intracellular environment, if we allow positively charged ions to come into the cell, right, which is then going to make the inside a little bit more positive and the outside a little bit more negative, it's basically going to kind of weaken the overall magnitude of the resting membrane potential. That movement of that positively charged ion, letting it come into the cell, actually leads to a release of energy whose magnitude depends on the value of that resting potential. Right? So what we're basically saying here is that the resting membrane potential is a source of free energy for the cell. You've probably actually seen this equation here in the bottom left before. This is probably going to be a first-year chemistry thing maybe. Maybe you saw it before that. But this equation reminds us that there's a relationship between membrane potential and free energy. Changes, delta, in the membrane potential lead to changes in free energy. And you can see the little negative sign here. There's kind of an inverse relationship, which is to say that if we decrease the magnitude of the resting membrane potential, that releases free energy. And then the converse is true too. It takes free energy to increase the magnitude of the membrane potential. So it's important for us to appreciate this relationship that, the further away the resting potential is from zero, right, which would be no resting potential, the further away that the resting potential is from zero, the more energy that is stored, the more free energy that is being stored by the cell in the form of that resting potential. And as the membrane potential goes further and further away from zero, there's more and more energy being stored there. And as the free energy, or as the resting potential gets closer and closer to zero, you are releasing more and more of that stored free energy. So this explains then why all cells have a resting potential, because it gives them a source of free energy that can power work in biosynthesis, as it says here, especially work in biosynthesis happening in proximity to the membrane. And so this is a reminder for us that not all cellular work involves ATP, right? Sometimes we're almost taught to worship at the feet of ATP like it's the God Almighty energy currency of the cell. But it's just one energy currency in the cell. Yeah, it's a common one, it's used in a lot of ways, but it's not the only one, right? There's the resting membrane potential, and there are others. So it's important for us to keep in mind that ATP is just one energy currency. It's like when you think about how can you pay for food at La Prep or something. I could pay cash, I could pay credit, debit, my phone, whatever. Bitcoin maybe they'll take over there, I don't know. But it's many different energy currencies that exist within the cell, like we have many different ways to pay for food. And so the membrane potential represents another free energy source for the cell in this case. I want to give you a practical example of this. Like, where in the cell would we actually use this resting potential free energy to power something? Well, let me introduce you to this guy here in purple. This is the sodium glucose cotransporter, SGLT. The sodium glucose cotransporter, it does exactly what its name would suggest. It cotransports glucose and sodium. So the idea here is we can use this cotransporter, cells can use it to take up glucose from their environment and bring glucose into the cell, even if there's not a favorable concentration gradient for that. Even if there's just a little glucose in the extracellular fluid, and even if there's a lot of glucose in the cell already, we can use this transporter to power the active uptake of glucose. And you don't see ATP anywhere in sight here, because what's being used as the power source is that sodium cotransport. right? That positively charged sodium is allowed to come into the cell with this SGLT. That's going to lead to a reduction in the magnitude of the resting potential, which our equation says will then release free energy, and it's that free energy that powers the glucose uptake. So we don't have an ATP involved here in this process. We are using the free energy of the resting potential and the movement of this sodium ion that reduces the magnitude of that potential in a way that releases free energy, and then using that free energy to drive the uptake of glucose. The other thing I think we have to just be explicit about too, and I think I already was a little bit, but again, if we reduce the magnitude of the membrane potential, that releases free energy, and we've just said that we can use that free energy to do things like power glucose uptake. The kind of corollary of that, the flip side of that, is that if we want to increase the magnitude of the membrane potential, again, free energy is required, right? So, free energy is required to generate and also maintain the membrane potential, right? As they say, ain't nothing for free. If you want to have this resting potential, this source of free energy in the cell, you have to be investing free energy to generate it, and then you kind of cash in on it later when you want to do work, right? So, if you think back, I don't know, if you took Bio B34 with me, we talked there about the leak of sodiums and potassiums across the membrane, and then you have to spend energy to pump those ions back. I mean, that's what we're kind of getting at here when we say, hey, it costs energy just to maintain the resting potential, right? Because we have to maintain these ion differences across the membrane that drive the movement of the ions across the membrane to create this membrane potential, right? And so, yeah, we have to put energy in to maintain and generate the resting potential, but we can also then extract free energy from it to power various work in biosynthesis. Another thing that's very important for us to appreciate just in general about the resting membrane potential is that not only does its value depend on, say, just the raw number of charged species that actually have moved across the membrane, right? If you think about, okay, obviously if I have one potassium leak across the membrane into the extracellular fluid, that's going to give me some value of membrane potential. But if I have 10 of them leaking across, I should get a bigger value for my resting potential. If there's 100 leaking across, it should be even bigger, right? So pretty intuitively, the resting membrane potential, its magnitude will be dictated by just how many charged species are moving across the membrane. But additionally, and this is all coming from Coulomb's law, it says, is that the closer the two fluids are to each other, the closer the extracellular and intracellular fluids are to each other, so essentially the thinner the plasma membrane, that also increases the magnitude of the resting potential. If you think about the resting potential as kind of the energy that is stored, in the form of this separation of charges across the membrane, right? You've got positive charge groups on one side, negative charge groups on the other side. There's energy that is being stored in that kind of separation of those charges. What you can probably then quickly envision is that if those charges are right close to each other, separated only by a very thin membrane, those opposite charges will perceive each other so strongly because they're so close that they'll be like desperately wanting to get together, so they'll have a lot of energy. But if you keep them widely apart from each other so they can't really sense each other much, then there won't be really a lot of energy there. They're not too eager to come together. They don't care that there's a charge separation because they're so far apart. It's kind of like if you imagine that you had like two people who hated each other, for whatever reason, like a Blue Jay fan and a Yankee fan, just to kind of like keep your mind away from anything else. Right, so you got a Blue Jay fan. I don't see any Yankee hats in there. I know Yankee hats hiding in here. Are there Yankee fans hiding in here? I love New York. Is that the closest I'm going to get? Is that what it says? Ooh, okay, yeah, that's right. Cover that up. But imagine if you had a Yankee fan and a Blue Jay fan like right close together. They're sitting in adjacent seats at the ball game, right? Their hatred is going to be so palpable, that there's going to be so much like tension and energy there. But of course, if you have them sitting miles apart from each other and they have no interaction, there's not going to be that same intensity. So this is kind of what I'm getting at here, is that the thinness of our plasma membrane, because the plasma membrane is very thin. We're talking about 7 or 8 nanometers on average. So these charged species, these potassiums and sodiums and other ions that are separated across the membrane from each other, they're so close because they're only nanometers apart that it doesn't actually take too many charge differences to actually create that resting membrane potential. They're so close together that it's like having like just two Yankee and Blue Jay fans apart from each other, but they're so close that there's so much hatred right there. That's different than if we had them widely separated. So the point I'm trying to get at here is that because the plasma membrane is so thin, right, you actually don't need that many actual ions to be separated from each other across the membrane to get a significant resting potential. And that goes back to my earlier kind of approximately addition to the law of electroneutrality. We're not really talking about a substantial number of ions that have to move across the membrane to create this potential. We're not talking about really any significant number of ions, any significant deviation from that law of macroscopic electroneutrality, because the thinness of the membrane means only a few ions have to move across to create that resting potential, that big charge difference. And kind of going along with that still is the idea that, again, because the plasma membrane is so thin, if we want to change the value of the resting potential, right, going from resting to graded, for example, as we talked about earlier, you actually only need to move a few small number of ions across that membrane to do that. We have this way of talking sometimes in nervous physiology, and I'm guilty of this too. We say kind of what are stupid things like sodium rushes into the cell. You know, and if I said to you, like, the first years are rushing into the room, you would think there's like all 500 of them crashing in, like, get the hell out before they stomp us all. But really, maybe it's just a few, right? When we're talking about ions, we're only needing a few ions to cross that membrane to make significant changes to the membrane potential. Again, that's a consequence of how thin the membrane is. So we really need to make sure we keep that in the back of our minds at all time, right? When we're seeing, even in an action potential, and you see these big changes in the membrane potential value going from, say, -70 to +40 or something, it's a big looking change, but the actual absolute number of ions that cross the membrane to cause that change is almost insignificant. It's such a small number. So we should be more precise probably with our language in nervous physiology. We shouldn't say dumb things like, sodium rushes into the cell, because it creates this connotation that there's a huge number of these ions moving, but the reality is we can establish resting potentials and change membrane potential values with really almost insignificant numbers of ions having to move across that membrane because of its thinness. Okay, I will stop there. We will continue on Thursday. We'll actually get into a little bit, we'll keep talking resting potential. We got a lot to talk about. I'll see you then.